Good evening, everyone. My name is Aveen Dayal. I'm a PMRF scholar and also a PhD scholar at IIT Hyderabad, and I will be conducting these live sessions for the course Deep Learning for Computer Vision, taught by Professor Vineet. I'll just share my screen and we can proceed with this week's session. I hope my screen is visible. Maybe someone can confirm in the chat. Yeah. Maybe can someone confirm if I'm audible? Yeah. Okay. Thank you. So this week basically we'll be talking about um, concepts related to the week 10 lecture, which was variational autoencoders, generative adversarial networks, and also a combination of both generative adversarial networks and variational autoencoders. So I hope the recorded lectures have been studied by you people. So first, I want to talk a little bit about generative models. Like what exactly are we trying to achieve with generative models? And then maybe I'll talk a little bit more about the GANs, what is the architecture, and what should be the loss functions. And then we go into a similar concept for which uses generative modeling. Another algorithm is variational autoencoders. So we then talk about those, and then after that I'll explain a brief code walkthroughs for both of these concepts. So before beginning, what exactly are we trying to do in generative modeling? So up until now, previously we talked about classification, different tasks like classification or clustering, or for that case, any other task if you take in classification also. All of those tasks can be done in two different ways. One is discriminative learning and one is generative learning. So if you think about what discriminative learning does, so we assume that the posterior distribution, which is the probability of a particular label y given a particular input sample x, we have to basically at the end of the day learn what this distribution is. So now learning this distribution can be done in two ways. Either we can learn it discriminatively or we can learn it generatively. So, what do you mean by discriminatively is that we assume a certain model, like a linear model, we assume, or we assume a non-linear model or a compositional model, like a neural network. So we assume a certain model with certain parameters, and we directly learn the posterior distribution. That is called the discriminative model. Whereas in the generative model, we first learn the other distributions, likelihood and the prior distributions, which is probability of x given y and probability of y. We learn or we model those distributions, and then we infer the posterior distribution from after learning the likelihood distributions. So in generative models, we try to understand how the data has itself the distribution which it is generating, right? We try to model that particular distribution. So why is that modeling important? So if you can look at this example, so if you have the image A, which is a picture of one of the European cities. So if this is our original image we have. Now if you want this particular painting to be have some other artistic characteristics, like you can see, if you see B, it has a more dark or gloomy side of that particular painting. Or if you see the picture C, which is very similar to what Vincent van Gogh's painting Starry Night is. And these are different artistic forms basically which are possible, and we want our original input, which is our picture A, to have these particular different art forms. So if you learn a discriminative model, we can't do such things because it is not possible for the discriminative model to understand what is the underlying distribution which is generating the data, which is generating this particular image. So we are not learning that. So if you don't understand that, we can't modify it into different art forms. So for such particular sample generations, we need generative models. So this is just one example. Like you can think about Chat GPT. That is the most basic example I think I can help you understand. For generative models is Chat GPT or LLMs, which we use nowadays everywhere. So those are basically content generators. So all of them work underlyingly using these concepts basically of generative modeling. So to talk a little bit more about the difference between the discriminative and generative models. So if you can see, like I said, on the discriminative models, if you have two classes, your red class and your blue class, and discriminative models basically we try to find this particular line which is separating these two. So the posterior, we no longer we assume that the posterior itself like is equivalent to some what do you say, a model or like a linear model or like a non-linear model, and we basically find this decision surface by the back propagation of the neural network, and we try to find this decision surface which separates these two classes. So here we're directly estimating the posterior distribution. Like I said, since we just find a separation between these two classes, we are no longer trying. If someone asks me how will a sample which is in the red class but somewhere over here, how will this particular sample look like, the discriminative model can't explain. Whereas generative models, we don't want to separate them, but instead we try to understand the entire distribution of this particular class, blue class, the entire distribution, how it was generated, the red class. So next time if someone asks me, okay, what if I want to generate a sample from this blue class which I've never seen, but it has certain characteristics, how will it look like? Then we can easily generate it because you understand the underlying distribution with which this particular blue class has been generated. And to give some examples of the models, so these are standard all machine learning models, not just deep learning. So discriminative models are usually logistic regression, random forests, SVMs, your neural networks, decision trees, k nearest neighbors. Whereas generative models, in our case, is basically hidden marker models, naive bayes, Gaussian mixture models, linear discriminant analysis models, and Gaussian discriminant analysis models, Bayesian networks. These are all generative models. And in terms of deep learning, in our particular course, we cover more models like autoencoders, variational autoencoders, and then generative adversarial networks. These are again all generative models. So I hope this difference between the discriminative and generative models and the motivation for generative models is clear. So next we talk about GAN models. So in this particular case, I have tried to summarize all the like parts of the GAN model in one particular diagram. And as you can see in this case, we use a DC GAN. So difference between a DC GAN and a normal GAN is DC GAN consists of a deep convolution layers, whereas a normal GAN doesn't have to be convolution layers. It could be just a normal MLP. In this particular image which you see, it's a DC GAN basically. And what we try to do in this particular GAN, so as the steps are clearly marked, we first assume some prior latent distribution, which we call the vector Z. Uh, and then we sample prior uh, latent variable Z from a distribution P of Z given a particular X. So we assume some prior, like usually it's Gaussian. So we sample this vector Z from this particular Gaussian distribution, and then we have a generator. And in this generator, since we're talking in terms of convolution images, right? So in this particular generator, we will try to upsample from this vector or this particular smaller image into a image of the input size. Like for example, if I have an input size of 224 comma 224, which is my X over here, so from this latent variable Z, which is of a smaller dimension, we upsample it to 224 comma 224, which is the input dimension size, which is the X size. And then this G of Z is basically that particular generated image. And then we send this generated image G of Z and the original image, which is my X input, uh, to the discriminator. And discriminator again, basically it has a normal convolution process where you take these two samples and then you keep on reducing the spatial dimension, and then finally you end up with with the final vector, which we can either have two outputs or you can have one output. But what we want to do in that final output is we have two classes, basically a real image and synthetic image. So we basically classify these two we classify the G of Z and X into Either it's a real image or a synthetic image. Make sure that when I say g of z and x are going to discriminator, they're not going at the same time. So you can think of it as like one after the other. Basically, the training loop happens. First we send x and then we send g of z. So it could either be g of z first or x second. But what we want to try to do is we have to train this discriminator to basically for it to learn whether the input which is coming, whether it's a real image or whether it's a synthetic image. So that's what this discriminator is trying to learn. So all in all, this is the training that is happening. We want the generator to basically generate an image which the discriminator can't distinguish whether it's a real image or not. So that's the goal of this particular generative adversarial networks. So why the term adversarial networks? Because here we have competing players. Like if you consider generator as player one, discriminator as player two, we have two players who are competing for winning a competition, which is basically generating image which is as close as possible to the real image, but which is not seen in our particular input sample. So that's why this adversary is happening. That's why we call it the adversarial networks. In mathematical terms, this adversary is basically nothing but the min-max optimization. So whenever you hear the term min-max optimization, it is always a adversary network. It doesn't have to be GANs itself. It could be any concept like this min-max optimization comes from convex optimization or it comes from game theory in specific to be specific. So where you have two players competing to win a competition. So one has to minimize a certain objective, one has to maximize a certain objective. So this entire GAN architecture is inspired from the game theory concept itself, the training of this GAN architecture. So this is the loss function which we use. So I will explain intuitively how the loss function works. You can always look into the recorded lectures of how it is derived and everything. But I wanted to give a very intuitive understanding like what exactly are we trying to do over here. So if you look at the first term, we have this particular log of discriminant output for this particular input x. So here what we're trying to say is forget about the log for a while because log is just used for faster optimization, but you can ignore log for a while. If you look at this, all we want to try do is we want to maximize the D output whenever we want to maximize the output of D whenever the input is coming from the real sample. So like I said, D has only two outputs possible, 0 and 1. So for this particular case, we assume 1 is real image, 0 is synthetic image. So D can output 1, which is a real image, or it can output a 0, which means that particular input is a synthetic image. So we want to maximize D. So we are trying to maximize D. That is the first term. So we are saying that we want to get as maximum value as possible, which means the maximum most possible value for D is 1. So we are saying that whenever the input sample is real, the D should basically say it's a real image. And at the same time, we are saying if you ignore the minimum G for a while, and if you look at this particular second term only in terms of X, just assume G is constant for a while. So here what we're trying to do is we want to maximize D with respect to this 1 minus, maximize D with respect to this function, which is 1 minus D. So here the maximum possible value is when it if D is maximum, then this will become 0. So sorry, if you want to maximize this, it is maximum only when the D is 0. Then this 1 minus D will become 1, which is the maximum possible value. So when will D become 0? When it says that this particular input is a synthetic image. So all we are trying to tell the max player is that when X is coming, you say it is 1. When from G of Z it is coming, you say it is 0. That is what this particular maximum operator is trying to do. If you look at the minimum operator, what the minimum operator acts on the parameters G. So the minimum operator then says, ki, I want to minimize G with respect to this second equation 1 minus D of G. So how to minimize this? Minimization is possible for this particular 1 minus something. The minimum possible value is when this particular D of GZ is the minimum, it's the minimum possible. So it's the maximum possible, which means that D of GZ should be 1, which means that G of Z should be generated in such a way that is discriminated as saying that the output is a real image. So I Hope I was clear when I was trying to explain what this min and max is trying to do. Maybe I'll just pause for a quick 1 minute and maybe you can just ask me if you have any questions if that particular intuition was clear. Uh, Maybe I'll just quickly once again say it and then we can go ahead for the next concept. So again, so what max is trying to do is it maximizes this first function, whereas it means that the d should be 1, then only it will become maximum. Whereas the second function maximum will become when the output will be 1, and that is possible when d will become 0. That is true because that is what D wants to do also. It basically wants to distinguish the G sample to be synthetic. It means it will output as 0, which means that the final value will become maximum. Whereas for in respect to the parameter G, if you want to minimize some like a term, second term with respect to G, we want the second term to be as small as possible. And as small as possible is only the least value that is possible is 0. And to get 0 we want d of g of z to be 1, and if you want d of g of z to be 1, g of z should generate an image which is exactly like a real image so that d will say it is 1. So that is what this min and max is trying to do. And apart from this particular loss function, which is the like the vanilla GANs use these loss function, over a period of time different variations for GANs have been developed. Like there is WGANs, there is MMGANs. The WGANs is called Wasserstein GANs, so you can always look into that. It's a very interesting type of extension to normal GANs. It uses Wasserstein distance. Explanation of Wasserstein distance is beyond the scope of this particular course, but you can always look into what Wasserstein distance does. It's like KL divergence, like GANs. At the end of the day, this optimization function, if you see the recorded lectures, you inherently are trying to minimize the KL divergence. That is what this optimization function is trying to do. Whereas in WGANs, you don't do KL divergence minimization, you do Wasserstein distance minimization, which is a better similarity metric than KL divergence. Apart from that, there are again several other GANs. You can just always look into the particular paper in which these GANs are proposed, because most of them are minor improvements, but all of them baseline they use this particular concept of min-max optimization. And then we come to another concept called variational autoencoders. So in GANs, as you can see, whenever we are trying to generate new images, right, like the G of Z, nowhere have we assumed what a particular latent distribution should look like. Like we assume there is a prior Z, true, but we didn't assume any other things like, okay, what is the P of Z given X, that distribution. We not assumed what the distribution should be or what are the different modes in the distribution. We're not thinking about those things. We just say, okay, there is some prior distribution and we are trying to generate from that entire space of prior distribution. We're not exactly modeling it. So this is called as implicit modeling. Whereas in variational autoencoders, that Z distribution from where, sorry, the Z sampled from a distribution, right? That particular distribution, we try to model it. And that is where you see the middle part. So in the middle part, we assume that the particular prior distribution, which is P of Z given X, that particular thing will have a mean and a standard deviation, and we try to figure out what is that mean and standard deviation. Why only mean and standard deviation? Because we assume it to be a normal distribution and then we proceed in that way. If you don't want to assume it to be a normal distribution, then the derivations and all, it will become a little problematic. So for simplicity's sake, people assume it to be a normal distribution and go ahead with that. So in variation autoencoders, we try to explicitly find out what the distribution is by identifying the means and the standard deviation. Then we sample a particular Z from that distribution, which is our latent variable. In GANs, we don't do this, what you say, learning of the distribution. We just assume Z to be coming from some space. And from this Z, we again have the decoder network, which will basically generate that particular input X. So all in all, if you look at this picture, we have the forward propagation where X is given. In this case, it could be an image or any vector, but in particular image, you can see it's a vector. We basically use a encoder network which is trying to model q of z given x, the distribution q of z given x. We model this distribution by learning the two parameters mu and standard deviation. We add a little bit of noise. This noise is this particular type of adding of noise is so that we helps it in sending the back propagation gradient signals. So you can always look into reparameterization technique taught in the recorded lectures. So this part we add so that we can easily send the gradients from the decoder network to the encoder network. And then once we more learn this distribution and the mu and sigma values, mu and delta values, we then sample a z from this, and then we decode it. That is basically upsample from that d space, and we go up to the yeah we sam sorry we decode it, and we then project it onto the original x vector, and we say ki how close is this uh, upsampled x, like output x bar, and to the original x, and then we use mean square loss to identify along with KL divergence. Sorry, I think there's a question by Bhupendra. um,
Hello.
uh, yeah, yeah. What?
I asked this question in the discussion form, but I did not get any reply. So I thought I will be putting it here so that you can uh, get it reached to the professor personally.
Okay, what exactly is your question?
The question is, whenever I am doing this, so in adversarial autoencoders,
Okay,
the real sample which we samples from a Gaussian noise, right?
okay,
That is given the discriminator as to compare the sample which is generated from the encoder. So this is a ground truth sample which we samples from our Gaussian noise. Okay.
okay, okay.
So the dimension of this sample and the dimensions of the sample which are coming from that, or the dimension of latent stress which is coming from the encoder part, are not equal.
You're talking about, no, no, for the Gaussian noise which you are getting, we are adding it for the reparameterization. You're talking about that.
No, 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 no. This is variational autoencoder. I'm not talking about variational autoencoder. I'm talking about adversarial autoencoder where we have some.
Okay, 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 okay. I think maybe we can discuss it about it when I come to that.
Oh, no, sure, 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 sure.
Yeah, sure. Yeah, you can. Yeah. So sorry. So getting back to this variation autoencoders. So here, so the concept is simple. We have our input x. We have an encoder function which learns this distribution z given x in terms of the mu and sigma, and we add a noise, Gaussian noise, to this sigma term, and then we sample a latent variable z, and then we do a decoder and we generate an output, and we see how similar these two outputs are. In VAEs we mostly use a MSE type of a loss, and to compare this x and x bar, and then we have to minimize these two distributions, which is done by minimizing the KL divergence between this q of phi and p of theta. And this particular loss function is called the elbow loss function for variational autoencoders. And once we get the loss function, we back propagate it uh, like we do for general neural networks. So I hope this is clear. If there are any doubts, you can unmute and ask, or you can put it in the chat. Maybe I'll just pause for a quick 1 minute. If you have any doubts, please ask me. So, quick example would of what exactly the VAEs are trying to do is by looking at this particular image. So, if I have an image which a person is smiling, and there are so many other features, right? Like the hidden features, which we call latent variables, like his skin tone or his particular gender, whether there's a beard or not, whether he has glasses or not, hair color. I mean, these are not the only latent variables, but there could be a lot more. So all of them, that is what we're trying to encode when we do this particular distribution and we sample this variable, right? This is what we're trying to do basically. We were trying to see at what position is this particular latent variable, like what is the distribution of this latent variable, what is the distribution of this skin tone latent variable, and all of them you can see are assuming a normal form because we start off with that assumption that they are normal distributions. So at the end of the day, you can find that okay, if I get an input like this, the particular latent attributes will have these particular uh, values. And now if I want to generate an image which has less smile, a darker skin tone and he's a female and has no beard and has no glasses. So we just keep on, it's like plug and play. You keep on moving the distributed values here and there, and the output you get as a different image which you want. Like at inference, basically you get an image which you set these particular values at. So this is what inherently variational and autoencoder is trying to do. But as you've seen, one problem with variational autoencoders was this: there'll be a lot of holes in the manifold. Like it is not a continuous smooth learning happening, but there are a lot of gaps in between each of these latent variables when they are trying to learn. So because they here we are assuming this explicit distribution, that is why there are some gaps, or we call it diffusion, diffusively spreading the mass of that particular distribution is happening across these latent variables. Whereas in generative adversarial networks, since we don't assume any distribution as such, and so we kind of take continuously from all the latent space. Like we don't say ki, okay, variable is for approximating this distribution, so we take only these values. It's not like that. We take a more of a continuous spectrum in that latent manifold. So this is one of the limitations of variation autoencoders also. And moving ahead, we have a small difference between what exactly autoencoders and variation autoencoders do. So in autoencoders, although the concept remains the same, that we try to learn a latent variable at the end of the day. Here also in autoencoder, initially we saw that there's an input encoder, there's some hidden layer in between which we call the latent space, and then we decode it, and we want, like, we use some loss function to say that the x and x hat should be the same. But the difference with variation autoencoders is this distribution, modeling of the distribution of the latent space. There's two blocks, extra blocks, which you see. That is the only difference between variation autoencoders and normal autoencoders. With this addition, modeling of this particular latent distribution, we get more control, and we can generate more of this data, more of different diverse data, which we have never seen in our input sample. And then coming to adversarial networks, adversarial autoencoders. So adversarial autoencoders, like you can see, it is a combination of both VAEs and also the combination of GANs, basically generative adversarial networks. So the first part on the top, you can see it's a standard variational autoencoder where you have your input X, you have your encoding network, you have your latent Z, which we are trying to learn, and then you have your decoder network, which will generate the output which is similar to the input. The only difference is in this particular Z, we previously we used to learn using KL divergence. We used to try to figure out. We tried to minimize that loss, but now we say ki, okay, let's assume a prior P of Z, like we assumed for GANs, and then this Z which we are modeling, this Q of Z given X, and then we are sampling a Z from this Q of Z, right? This Q of Z and this original real P of Z, which we are assuming some prior, are these, what is this Q of Z learning? Is it as close as possible to P of Z? That is what we are trying to do. So what we are trying to say is the latent distribution which we are learning, is it as close as possible to our prior, some arbitrary distribution, we have some prior knowledge about the task? Is it as close as possible to this P of Z? And adversarially, how can you say if these two are close, like if it's a real or a synthetic image? You can see that if you want to compare these two things adversarially, we send it to a discriminated network, and if we fool the discriminated network, then it means that we are able to say that this particular Q of Z is very close to P of Z. So if the discriminator is not able to, if the discriminator is able to separate these two, then it means that Q of Z is not close to P of Z. So in this way, we now don't have holes or the diffusion which I talked about. Now we have a more continuous Q of Z space, because we are trying to model Q of Z from a prior P of Z, which is more continuously distributed across the entire latent manifold. So yeah, this is the basic working of the adversarial autoencoders. So maybe I think Bhupendra, now you can unmute and ask your question exactly, so we can discuss it right now.
Yeah, so my question is at this input block,
Mhm.
we are feeding the input from my this variational autoencoder part from the bottom, from the top up, from
Yeah.
my distribution of, I mean, latent space is coming from QZ, right?
Right.
and the other is my drone sample from PG, which is my real distribution of my data.
Okay.
So when I'm feeding these to my discriminator network,
Okay.
and then my discriminator says me, yeah, whether it is real or fake, right?
Okay.
So the samples which I'm drawing from my original distribution, and which is given in this assignment, is a Gaussian distribution with the mean 0 and variance 25, if I correctly remember it.
Okay.
Yeah. So the noise dimensions which the code samples is 128 cross 96 or 76, but the samples which are coming from the latent space of my variational autoencoder
Mhm.
are 128 cross 24, because the latent size is 24 there, right? So 128 is my batch size. Hmm?
Yeah, 120 is a batch size, so it should be same. It should be 96 only.
Should be 96, but it is not 96. So this is what my doubt is, because otherwise the two questions would go wrong. The last two questions of the assignment.
Okay, maybe I'll try to take it up with the person in charge and let me see. Because as far as I remember, I think see they have run this experiments multiple times when they set the assignments, the processes. They run it multiple times on the collab notebook and they check for all these errors. So
Okay.
um,
Probably I may be wrong, but
yeah,
the expected answer is, or the expected dimension is 128 cross the same dimensions
yeah.
in the
Input to the discriminator should be the same basically.
yes, right?
Yeah. So maybe just
Maybe I
check maybe just
yes.
check again once again you also clearly because has anyone else also raised felt or faced a similar error or something, because this is more of a coding like question error, right? It's not about uh, coding error or
It's not
something.
yes, yes, yes.
So did anyone else also face it in the discussion forum? Did anyone else also face it?
No, in the discussion forum, I only raised this doubt, but no other person has raised this. Probably I'll check it out again and
Yeah,
I'll
sure.
reply in discussion form. So please keep an eye in the discussion form.
Sure, I'll also ask the person in charge to also check once, but as far as I think, if no one else is facing this problem, then maybe you will check once again. Maybe you
Yeah,
can.
yeah, check.
Okay. Anything else? Any other question?
No, no, thank you.
Thank you. Any other question from anyone else related to the concept behind adversarial autoencoders or any other BAEs or GANs? Okay. So maybe I'll just quickly summarize these and then we can move ahead with the what is a code walkthroughs. So to summarize, basically in generative modeling, these two is what we've talked about. One is the generative adversarial networks, and one is the variation autoencoders. And apart from that, there is a more recent modules, something called as diffusion models, which is not yet covered in the course. But I think it's important for you to know because diffusion models are doing really well, especially if you look into models like DALL-E, and I think there might be other models also. So these are very good. Like Chat GPT is to text, right? Like Chat GPT can generate a very good text contents related to textual data. DALL-E is something which is very good for generating content related to image. I think it does even video. And DALL-E majorly it works on this concept of diffusion models. So maybe I'll try to explain it quickly, but it's a huge concept. It will take time, but maybe I'll just give you some brief idea about what diffusion models are, so that since it's a state of the art, I think it's a very good thing to have idea of what diffusion models are doing. So if you look at the diffusion models, so their concept is like in GANs, right? In GANs, we initially start off from noise. Like if you look at GANs, so if you look at this particularly, this particular P of Z is nothing but noise at the end of the day. Like if you imagine, if you take it in a pixel wise, each pixel will be some random value. And if you combine that entire, all the pixels 224, 224 and visualize it, it look like some blurry, not even blurry, it doesn't even make sense. It's just some random noise like you used to see static noise on TVs in olden days, right? It will look something like that. So what these people said is ki, if x naught, which is my initial state, is the noise state, is that a image like that static noise image is my x naught, and So x naught will be sorry x zero is my input image. Sorry, x zero will be my input image, and then I keep on adding some noise. Gradually, I keep on adding Gaussian noise, such that it goes to an extent that my final output will become that static noise. And then we try to reverse the process and identify from that static noise how much, if I keep on removing some certain noise, is I'm able to see that this particular image is actually making sense. So in a way, if you can imagine, it's like take an original image, keep on adding noise till you get a completely noisy image like the static noise, and then these two steps, basically the forward step is this, and backward step will be you keep on removing noise from this static noise, and you see at what stage with these two things where you're adding noise and removing noise are kind of forming an equilibrium. And at that stage you can say ki, okay, these are all the important hidden values that are needed to explain this particular image. So you keep on doing this for a lot of different images, and you learn the hidden variables that actually represent the particular input image. So we learn that underlying distribution. So it's an interesting concept. People have used a lot of variations over this simple idea. You can always look into so many blogs available. And apart from that, we've covered GANs, which is the adversarial training, and VAE, which works on minimizing the elbow function, which is the variation in lower bound. And yeah, any questions or anything? If there are no questions, we can go ahead with the code walkthroughs. Maybe I'll just pause for a minute. If you have any questions, you can ask me now. Okay. Then I guess then we can start with the code. So in today's code, basically, I wanted to talk about two coding problems. One is the DC GAN, how DC GAN works, and then one is the related to the variational autoencoders. So like I said, the difference between DC GAN and GAN is just that in DC GAN we use convolution neural network. In the normal GANs we just use MLPs. Uh, so here you can always I'll share this. You can always read the contents which are explained. So it's basically description of what a GAN and what does a generator do, what does a discriminator do. So you can this is the main optimization function which I explained. So we basically make the GANs train using this min-max optimization function, and we'll also see how you can use binary cross entropy actually to basically model this particular loss function in PyTorch. So like I said, DCGAN is basically extension of GAN, but uses convolution and convolution transpose. Convolution transpose is basically the upsampling of convolution. Like don't we don't use the word deconvolution because it coincides with another signal processing terminology. So we call it transpose convolution. So make sure that when you not to use deconvolution in deep learning. It usually means a different concept in signal processing. So we call it transpose convolution. And I think in one of my previous live sessions, I did explain about transpose convolutions and how it works. So I think that is okay. If time permits, maybe I'll explain once again after the end of the code walkthroughs how the transpose convolution works. So transpose convolutions, like I said, it's used for upsampling, and it's used only in generator basically upsamples, right, from the latent variable. So generator uses all transpose convolution, whereas discriminator uses a normal regular convolution neural networks. And this particular, I think the paper is also mentioned. You can look into the paper also once you get to look at the collab notebook. And in this particular case, the input images which we use for this particular code is 64 cross 64 cross 3. And yeah, I think yeah, these are the important things to know. So like always, the first things we do is import all the important libraries which we will be using. Like I think at this point everyone will be familiar with what torch.nn is doing. And I think all the libraries which we previously talked about, all of them are used, like data sets, transforms for augmentation, and then matplotlib and numpy for uh, data arrays and like visualization of that data arrays. And then also by now you'll be familiar with the term like why we are setting the manual seed. It's basically for reproducibility and everything. So if you, I'll be just going through a bit fast because all these are concepts which we kept on covering in the previous live sessions. But at any point, if you do not understand anything, please let me know. So these are the inputs. So in this particular case, we like this basically we have a data set at a particular uh, what is it directory stored, and we want to load that particular data set from that library into the data sets uh, PyTorch structure, and then from that data sets we go into data loaders, which will basically divide my entire data set into the batches depending on my batch size, and then it does the loading of that batches into the GPU and download like removing that removing that particular batch from the GPU back into the CPU back into the memory. So all those things data loader takes care of. So I think these are all just initialization functions if you see. So first we mentioned what is the root directory of my particular data set, the number of workers for the data loader. Maybe just to keep it interactive, I've explained this before also. Maybe can someone tell me what the number of workers do in data loaders? You can unmute or you can just write it in the chat. What do you think the workers do in data loaders? Any guesses what it will do? Maybe I'll explain it. So workers are important in data loaders because, like I said, data loaders yeah, yeah, that's correct. Like Bhupendra mentioned in the chat, it's for attaining faster parallelization basically. So when you divide your data into different batches, now each so your data set will be huge. So you divided it, although you divided it into batches, you can't load that entire huge data set on GPU because if you think about it, GPUs come in what 8 GB RAM, 16 GB RAM, 32 maximum you go by 48, which is your A100 46 GB. I don't think you go beyond that because it's very expensive to create GPUs with a bigger memory RAM. So with a bigger RAM basically. So now 46 GB can only hold a certain thousand samples, like thousands of samples. I think around 100,000 samples or something. So and this is I'm talking again a simple small images like 32 cross 32. Whereas in real world you go you have 224 cross 224, and actually image size will be even bigger. We do augmentation and bring it down. We downsample it to 224 224. So such huge data, especially in images, videos, all of these can't be loaded on the GPU at the same time. So data loader actually does the same thing. Actually does this particular thing where it creates the batches and stores everything in the secondary memory. And when a particular batch is needed to train our neural network model, this data loader basically calls that particular batch onto the GPU. And then after the training happens, like the update step happens, it then sends that particular batch back to the secondary memory and again brings on another batch too. So this uploading and sending back that particular batch, it's a process which takes time. So the number of workers actually creates like the multi-thread processing happening. The workers are basically threads. You increase the number of threads, you increase the number of workers, this loading and sending back to the secondary memory will happen fast. So if whenever you're training, uh, you won't face this problem for this assignments at least, but when you're working in actual for real world data sets and everything, and when you're deploying your own models, when you're actually working with your own models and training in your own local systems, when you feel like the training of your model is happening fast, very fast, but the date loading of that particular batch is not happening fast. The main time crunch is happening at that particular step where we are loading the batches. Then you can always increase the number of workers to make it more fast. So it's always good to keep a time check of how much time is taking for the training to happening and how much time is taking for the data loader to load the batches, and based on that you can increase your workers. And yeah, after that you define your batch size, image size, channels also. And Then this is important because in GANs we used the initial Z, right? So what should be the latent size? So we fix that particular latent size to be 100. And from here only we basically upsample it to our particular input image, which is 3 cross 64 cross 64. And then yeah, the feature maps you want in your generator and discriminator, which is these particular values. And in this case we don't train it to complete success, like we just train it for 5 epochs just to see how the model is updating and everything. You can always increase your number of epochs to basically make the model more accurate. Maybe a quick question. So we always say that increasing number of epochs makes the model reach accuracy. So do you think uh, is it always necessary that the models should go on to, like, for example, if I have a model which is trained for 100 epochs, and if a model is trained for 200 epochs, is it always the case that 100 epoch model will be less accurate than the 200 epoch model? Maybe someone can answer. So my question is increasing the number of epochs always going to increase the accuracy? L- uh, do you think it is the case, or do you think no, or why not? Like, any explanation? Maybe you can unmute or you can put it in the chat. Okay, so not always is true, but do you think, why do you think it's not always? But because technically gradient descent algorithm we keep on uh, yeah, it's not exactly overfitting. We wouldn't say overfitting. I think it depends on the loss surface also, basically how good your loss surface is. Sometimes it could I'm not sure if you can call that overfitting, so I might be wrong over here. Maybe you can call it overfitting, but as far as I remember, it's mostly to do how the loss surface is. Sometimes you think you found a global minimum also, but the more and more you keep on training, you kind of what do you say, in a way you kind of go more in depth, but you actually shoot away from your optimum, and you again jump ahead, and then you go into some other local minimum. From your global minimum you get stuck in another local minimum. So all in all, I'm also not very sure the mechanics which happens, because people are also figuring it out. So we don't know for exact reason why this happens, but it's a seen trend empirically, at least, that it's not always necessary to have more number of epochs. So that's why an alternative for that is people basically say early stopping. So people use different early stopping techniques, like, what if you keep a track of your accuracy after every epoch, and it comes a time that for 10 epochs your accuracy is not improving, it's in the same range of plus or minus 0.1, 0.2. Then you stop your model, don't train further, because then the model can actually become bad. So there are different early stopping techniques which you can always look into. That's actually very helpful, especially when you're deploying your models in real world. And then you have your different other hyperparameters like learning rate and Adam optimizer, hyperparameter betas and everything. So this is a particular data set called Celeb A data set. So I think this data set basically consists of all the celebrity faces, people faces, and I think yeah, I think there are a lot of number of, yeah, samples is like around 1,62,000 samples. And like I said, we use the image folder. We This is a standard image folder. It's a data set type which basically loads a particular sample from the root directory, and you can give your particular augmentations. Like, you have all these augmentations, which is first you're resizing the image, then you're center cropping it and normalizing it, and then from the data set you send into your data loader, and this data loader basically then splits your entire data set into batches. And again, this question I've asked previously also, but just to again iterate its importance, here we kept shuffle true, but what if shuffle is false? Do you think it still work? Any idea? So my question is, here we kept shuffle is equal to true when we are creating the batches. But if I don't want to shuffle, if I just, whatever my data I loaded, if I just keep as it is without any shuffling and create my batches, do you think our neural network model can learn, or do you think it won't learn? Maybe I'll answer. So it's always important. Yeah, it might learn wrongly, like Preeti has said in the chat. So it's very necessary. It's very important that the shuffle should always be true. It will definitely not learn if it's not true, because you can think of it in this way. Like for example, if you have three classes, each class has 10 samples, and so total you have 30 samples in your particular data set. Now I create batches, like every 5 samples I create a batch. So then you have total of 6 batches. So now when we are doing the training, so batch one, which will consist of only class one samples, because the first 5 samples are only class one, and the neural network will try to fit the parameters, because it has seen only class one. It will think that is the only data which it has to fit, and will try to fit that. Again, when batch two comes, it is all class one samples only. It'll get even more confident on how it is training, like what parameters it is choosing based on just class one, and then it will go further in the wrong direction of actual optimum. And then suddenly in the batch 3 you come up with a second class. Now it has never seen this class, so the gradient will be completely, like, it'll be huge gradient, because the loss will be very huge. And then because of that, the direction towards the optimum won't happen. So the gradient descent will actually not converge to optimum. It will keep on just going randomly here and there, because it's not seeing all the classes at one batch. It is basically seeing an iterative process, which is not a very good way. So it's always important that you shuffle your data as much as possible, so that at least in one particular batch you get almost all classes equally. It's not always possible, because sometimes you have class imbalance and everything, but you try to at least bring as much as possible, like as much as equality in the classes in a particular batch. And then after that, we have divided, like, sorry, we have created this device variable. So it's always important, like I always say, create a variable called device, which will basically link to what GPU you're using. In Collab we always have only one GPU, but in other like, there are possible cases when you use supercomputers and I think you have multiple GPUs. So keep track of which GPU device you're using, and send all your images, like the batches and your model on that particular device. So it's always necessary that once they're on the same platform, either CPU or either GPU, then only the training will happen. Otherwise, training won't happen. And you can see these are some of the images of that particular data. So it's all celebrity faces. Yeah. Again, weight initialization is an important thing. You have to initialize your discriminator and your generator network. So there are different weight initializations technique. I think that is again a hyperparameter, but nowadays more or less people are using a standard Gulrot initialization, which is similar to Gaussian initialization. More or less people are kind of using that. But I think, yeah, weight initialization is an interesting topic for you to experiment when you do these assignments, or in general when you want to work around with the neural networks. Look at how weight initializations actually affect your model accuracy. And this is the generator model which we are going to which we're going to use. So we have your 100 Z's, then we project and reshape into this in this particular dimension, 4 cross 4 cross 1024. Then we do upsampling, basically the transpose convolution, and finally we get your 64 cross 64 cross 3. And in between you can just see like what each particular this particular block at the end of the day will contribute to this much big patch in the image. So it's just a visualization technique, you can see. um, yeah. So this particular network is what we are going to code over here. So we first create a class called generator, and this generator, like I always say, it should import the class called nn.module. So it's a PyTorch inbuilt class, which basically when you import this, you're telling the PyTorch program that this particular generator is a neural network. It's a module class basically, and whatever this module class has a template. It should have two important functions. Like I always say, the important functions are init function. Obviously any class should have an init function, and the second important function is the forward function. This is where your actual forward propagation happens. There is also backward, but most of the times, unless you write your own backward propagation of what a particular layer should do, you don't worry about backward function. You just worry about these two functions is what you have to do. Right, one is the init function where you define your neural network, and the forward function where you're given the input and where all that input should go, like which all layers that input should go. So, like I always said in the previous classes, also, there are two major ways in which you can create your neural network. One is you can create something called a sequential, nn.sequential. So, sequential, you can think of it as like a list. It's like a big list, and in that list, you could write all your layers, like what and mention. Make sure that the layers which you're mentioning has a particular order, so because the data will actually transfer that way. So you start off from your first layer, then your normalization relu, then you do your second layer, then you do your third layer, fourth layer, and final layer. So all these should be in the same order of what you want your network to be. And then since it's a sequential particular structure, then PyTorch knows that input, when you're getting the input in the forward function, if you just send it to this particular first layer, it will automatically take the output and send it to the second layer, take the output from the second layer, send it to the third layer. So it's a easy way to create a neural network. Another way to create a neural network is you define each of these layers separately. You give each of these layers a global variable, and then in the forward function, you yourself will manually take the output of layer 1, send it as an input to layer 2, take the output of layer 2, send it as an input to layer 3. Why do we use that? Like I always say, sometimes you want intermediate layers output to do some other calculations, or you want that intermediate layer, like in UNet architecture, if you guys remember, we need to send a particular encoder output and concatenate it with the decoder's output. So such type of things, for those things you can't use sequential, because in sequential we know that once you give the input to the first layer, you can't get any intermediate outputs. You'll get the output only from the last layer. So to get that intermediate outputs to do further operations, it's better to create in a different way where you create each layer separately, give it a separate global variable, and you call all of those layers in the forward function, and you manually send the data from one layer to another layer. So that is very important to know. And yeah, once you create your generator network, we instantiate the generator network like we do in any normal class in Python. So you just call that layer and you send it to the device and you give it a variable netg. And in this case, the apply weight. So here we initialize the weights. So if you don't do this particular step also, there'll be a default initialization happening. But since we do like we set the weights to some particular initialization which we are following, we just have to do net g dot apply and you give this particular weights. So this apply function basically assigns all the weights which you initialized using some process into the network which you just created. Make sure the like sometimes if you have some pre-trained weights taken from some other neural network, make sure that the architecture of that and this are matching, then you can use apply directly on this particular weight sorry weight assignment, then you can directly use apply. But if the architectures are not same, then the weight assignment cannot be. And if you just print your particular neural network, this will be the output. And then we define a discriminator network very similar to what same steps we follow but in the opposite direction. So and here we use normal convolutions because we want the discriminator to basically output will be whether it's a real image or a fake image. So it's a normal convolution. uh, yeah, and after that we just define, we apply the initial weights which we created, and if you just print, this is a discriminator network. Now comes the loss function for the generative adversarial networks. This loss function basically uses binary cross entropy, because here we just have two outputs from the discriminator, which is 0 or 1. So we use BCE loss. And as you can see here, we create two different labels. One is our fake labels, which is all zeros. And when I say labels, I mean ground truth labels, right? We need to set the ground truth labels because we're not getting any ground truth labels. If you look at the data set, if you look at this data set, there are no labels. We are not saying ki this is person one, person two. Here we just take the images as it is. We don't take any labels, and we generate labels. And what are these labels? If it's coming from a real image, we give it a ground truth label 1. If it's coming from an image which is from the generator, we give it a label 0. So that's why in the loss function calculation, we create two label sets. We call it the real label and the fake label. We set it to 1 and 0. I'll show you in the next course snippet how it will, how exactly are we creating using this BCE loss. So first we create a normal instance of this BCE loss, and then we have two labels, real and fake, and we create optimizers for both the discriminator and generator. And now when you're training, so we start off again. Like these are all epoch loops, and inside epoch we do for each batch. So this is a standard neural network training loop. And first, I always say keep it zero gradient. Uh, Maybe just a quick question: why do you think this zero grad is important? Why do you think this particular line is important? Net d dot zero grad. Any guesses? Why do we need that line? Yeah, like correctly pointed out, it's to clear the gradients basically. I wouldn't say basically. So what happens is previous update of the batch, there might be a possibility that the gradient values are still not completely sent to 0. Or there's some previous gradient values which might interfere with the next update. So we won't get the true gradients in that case. We'll get some pseudo gradients. So to remove any such noise or anything, we first make all the gradients to be 0 of that particular network of that particular weights, and that's why we call this net d dot zero grad. And then we get the data, we send it to GPU, like I always say, that's important. And then here we create the label. Now since it's a real image, we create the label of all ones. And as you can see, this particular line, what it does is we take the integer, since it's a real label, it's 1, and we create all ones. How many ones we'll create? Which is related to the batch size. So if we have in this case 128, so we create a vector of 128 rows, and all of them will have a value 1 because it's a real label. And then you send the image data to the discriminator, you get your output. And now here we can directly use the binary cross entropy, because it's the ground truth label, what your discriminator is outputting, and you can just use that binary cross entropy directly. And the discriminator error will just be this binary cross entropy. And then we update the discriminator net, and this is only one update. And next we do it for generator. In generator, we first generate a random noise, and then we send this random noise to the generator. We get the fake out, whatever image we created, which we call the fake image. And then correspondingly we generate a vector called fake labels in this label.fill. It is generating 128 rows. Again, all of them will be zero values because it's a fake label. And now this fake input will go to the discriminator, we get the output. And now your error will be again the binary cross entropy of this particular output and the fake label. And then we basically do a backward step, and final, you can see there are two errors which are happening. So yeah, here you have your final uh, discriminator error. Discriminator, as I said, it will be involved in two steps, right? Because we have in the loss function, if you see, this is a loss function. The discriminator will be at two steps. One is for the discriminator output itself, and one real input when it is taking, and when it is taking the g of z input. So there'll be two loss paths basically for the discriminator complete loss. So that is why here you see error d real when it is taking the real input, and what is the error when it is taking the fake input, and that will be a final error. And then we do the step. Basically, we update the discriminator. Similarly, we update the generative network similar way. We have only one loss over here, and that loss is basically error g, which is the BCE loss of the output and the fake label. And then we repeat the entire process for every batch and for every epoch. These are the sprint statements are just some just to keep a track of how the loss values are changing. So you can, as you see output. in each step, basically you print the loss of the discriminator, loss of the gradient, and so think this d of x and d of z is the d of g of z is the probability output, basically, whether it's a real image or a fake image. So yeah. So and then after this, you can just visualize the plots, and you can see the real images which were generated and the fake images. They're so close to how a real person look like. These are all generated from random noise, and it's actually very similar to how a human looks like. So this way you basically train your GANs. So any questions? If anything is not clear in the loss function, maybe I went a bit fast. Is the way how we use BC to train the GANs, is that clear? If you have any questions, you can unmute or you can put in the chat. I'll just pause for a minute. Yeah, if there are no questions, then we can move ahead to the second code. So here we talk about a little bit about the variational autoencoders, which is another type of algorithms which does generative modeling. I think first we talk a little bit about the autoencoders parts itself, and then from autoencoders we go to variation autoencoders. So I'll try to explain as much as possible. If you have any questions, or if you once you go through the notebook also, because we know that this is a bit confusing topic going from the equations, mathematical equations to the code. That's why there are a lot of explanations written everywhere for each code block, like what it is doing, what is happening. So you can always read through it properly, and if you have any questions, you can always ask me in the next class also. So first we talk a little bit about the encoders, autoencoders. So in autoencoders, we don't do any modeling of any distribution. It's very simple. We take the input, sorry, we take the input, we encode it down to a particular hidden state or hidden layer, basically this latent vector, and then this latent vector is then projected back onto a higher dimension, which is decoding, and then we get the output, and then we compare the input and output. Basically we want them to be as close as possible. So this is a basic concept used in autoencoders. So let's try to apply this on an MNIST dataset. Like always, import important libraries. I'll just skip through this part. We also create a device variable, send the to identify which GPU or CPU we are using, and then we create a small encoder network. It's a simple layer over here. We just take two linear layers, uh, like you can see these particular shapes. The latent dimensions, you can define what latent dimension shape you want, and then decoder will be the opposite of what this is doing. And these both are neural networks, and you can see very quickly very quick example of how to create it. Like you create two functions, init and forward, and in forward you basically take the input, flatten it, because the input is an image, right? So we flatten it to make it a vector, and here you're manually sending it to the linear one, and then you're applying a ReLU layer, and output you're again sending it to linear layer 2. So this is the second way of creating the neural network. The first way was using the sequential. So this is the second way which I was saying, where you manually send the input to layer 1 and whatever operations you do, and then you take the output and send it to linear layer. So this is the second way of creating a neural network. And then you create similarly for a decoder network, same concepts you use. And after that, yeah, you make sure that you reshape your output of your decoder into an image, right? Because we are initially taking the image, and then we are flattening it and sending into the network. And so we say that the output should be the same as input, so we need to make sure that the output basically again should be a matrix 28 cross 28 cross 1. And then we finally create the main neural network called autoencoder, where we call these two particular layers, encoder layer and the decoder layer. And then here we create our own forward function, where we take the input, send it to encoder. That z we create, we send the z to the decoder, and that is what we're returning. Again, a very simple training loop. You have your optimizer, which is Adam optimizer. First is your epoch loop. Inside that is your batch loop, and you take each of the data, send it to the device first, your zero gradient for you set your all your gradients to be zero. Then you send that particular X into your autoencoder. Whatever output you get will be your X hat. And this is a simple loss function. Maybe someone can tell me what this loss function is. I think it should be an easy guess. Maybe someone can type it in the chat or unmute and say what this particular loss function is, what I'm using. So this this line over here, what is this loss function corresponding to? X is my input, X hat is my output. So this is the mean squared error loss basically. So if you can see, sorry, this is the squared error loss, mean squared error loss. Yeah. So we are taking the sum also. So it's a mean squared error loss, which we are simply using between the input and the output. And then we do dot backward and dot step. Maybe yeah, like Jitendra message, it's MSC. Another quick question is, what is the difference between dot backward and dot step? I have talked about it in previous sessions. Maybe just to show its importance again, we'll talk about it. So maybe you can take a quick guess. What is the difference between the dot backward function and the dot step function? Why do we need to use both? Can we just use dot step? Okay, so the difference over here is when we do the dot backward, it's usually done on the loss function. So in a way, once you calculate your loss, loss dot backward will kind of tell the PyTorch, okay, this is the loss, and I've calculated the gradient with respect to my loss. And when the dot backward is done, all the other parameter weights which require the gradient, all the partial derivatives, they're all calculated and kept ready by the PyTorch. And dot step is where the actual update of each of the parameter is happening. So we need to call both of these functions. We call the backward to calculate the loss and the gradient with respect to that loss, and then we also tell PyTorch to get ready with all the partial derivatives, whichever parameter needs to update, it will have its corresponding partial derivative with it. And then dot step will basically do that updation of each of the parameters. So intuitively, you can think this is what backward and step is. And then after that, you finish your training for all the data samples and all the epochs, and you can just, I think you can just visualize it. So this is the latent space which we generated. So as you can see, the latent space is very clearly separable. Like all the ones are together, all the seven digits are together. Obviously, there are some here and there because it's not a perfect model, perfect encoding model. But more or less, you can see the encoder has done a very good job of creating different clusters for different classes. So maybe you can look at this image clearly, and you can see uh, how well an simple auto encoder can also model the MNIST data. And again, this is not any convolution. This is all MLP. We are not using any convolution. If you use convolution, the clusters will be even better because convolution, as you know, right, convolution is better suited for images rather than the MLP. So with MLP itself, you can model such nice clusters. So autoencoders in itself is a very strong neural networks. And you can see how the data is also being generated. So these are the outputs of the decoder. So these are different digits. Basically, these are the fours, two, zeros, seven, nine. You can just look at the outputs how they're being generated. And now once you understood autoencoders, then we talk a little bit about the variational autoencoders. So here you can see that once after the encoder layer, we have two other things, mu and this should be sigma, not mu. One is mu, one is sigma. We try to model these, and then we sample. We have add a little bit of noise after this. So that noise is the reparameterization trick, and then we sample a z from that distribution, and then we decode it. And then again we say that the input and output should be same, and then we have the loss functions, which is the MSC and the KL divergence. So we'll see how we do that. So this is the KL divergence loss for the Gaussian distributions between two Gaussian distributions. So this particular derivation, it's not possible for me to explain, but we there's a link mentioned on how this derivation has happened. So KL divergence between two Gaussian distributions is this formula. You can it's a standard formula. Derivation, you can look into this particular link. So again, very simple. So once you understand how to create a neural network, right? It's like, I think you can once you have the template in mind, it's very easy to create any big network because all of them follow a very simple template. Like again, here also you see the entire variational encoder. First we create two encoder decoder layers, and then we create the variational autoencoder class where we call this encoder and decoder. So first in the encoder, we again, there are two important functions, init and forward. Here we use the second type of creating the layers, where second type of creating the neural network, where we define each layer, and then in the forward function we basically uh, ourselves send the input to that particular layer and calculate the output and send it to the next layer. So as you can see, we calculate linear 1 output, we send it to linear 2. From linear 2, we basically calculate mu and sigma. So sigma is basically the exponential value. Sorry, from linear 2, we calculate mu, and this x, then we send it to linear 3, which calculates the sigma. And here is where we do the reparameterization trick, where z is equals to mu plus sigma into that small Gaussian noise. And then we calculate, okay, we calculate the KL value over here itself, the KL divergence between these two, but we'll use it later actually, this particular KL divergence loss function, but we calculate over here for simplicity. And then in the autoencoder class, we create a decoder layer. The decoder layer is similar to what we created in the autoencoder, so we're not defining it again. So the decoder layer will be same, encoder layer is different. And here we get our values. Basically, in the forward function, we send the input to the encoder, we get the z value, and we send it to the decoder. Training loop, again over here, as you can see, there are two loss functions which we are using. One is your MSE loss, which we saw in the autoencoder. Apart from that, we get the KL loss. So here the KL loss, we already defined it in the encoder, so you just access it in this way, dot 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 KL. Otherwise, you can also define outside also, but then you'll have to send those variables which you use to calculate KL, right? You have to just return it as an output from the encoder layer, and you can calculate it outside also. I think that is just a like whatever way you want, you can follow. It's just a type of coding. And then you do your loss dot backwards, and then you use your dot step, and you finish your training. So like you can see, the clusters are even more better over here. So you form even more good separation between the layers. You can always look again when you look at the when you get the collab notebook, you can look at it very clearly. And here, if you can see, it's even these are the outputs from the variation autoencoders, how they are generating the MNIST samples. So yeah, all in all, this is there, and there are also some other examples which like this is just for like playing around with the variation autoencoders. If you want to generate different kinds using the latent variables, like I said, you can, like I showed you an example of the smile person, right? You can move ahead the latent variables here and there, how to generate different samples that you can just see over here. So yeah, so this is what I wanted to explain for this particular live session. So if you have any questions, you can ask me, or or you can leave the particular live session. We'll meet next week. Thank you all for joining. If you have any questions, I'll be staying here. You can unmute and ask.